We are looking at some problems right now. So, we've got a Unit 3 C2 problem where objects are falling vertically or they're in free fall in some way. And what we're looking at here are, for problem 1, is seagulls. Seagulls are often seen at beaches, dropping clammed creatures like mollusks, shells, whatever. They're dropping them onto rocks. And the idea is that whenever you drop them onto rocks, they're going to open up and the seagulls get their food. So what we're asked in this problem is, if a seagull drops a shell from rest at a height of 14 meters, so from rest at a height of 14 meters, how fast, so what's the final velocity, is the shell moving when it hits the rocks? So we're looking for a VF here. Now the first thing we want to do here is draw ourselves a little picture, so let's make this beachy colors. So here's the cliff at the beach, and here's our seagull. The only way I can draw a bird is like this. And let's just doodle in the following. We know it's dropping the shell 14 meters, so that's a delta x we have. And what else do we know? That's it. That's the only number they gave me. So that can't be it. There's got to be something more. What's causing this shell to fall is gravity. We know gravity, g, which sometimes is written as an acceleration, or ag, or ay, whatever. And we know that's 9.8 meters per second squared. And we also know that initially this shell is at rest, so we know its initial velocity is 0. Now, we have a decision to make here, and you have to make the decision all the time. The decision is, do you want these, what direction do you want to be positive, what direction do you want to be negative? Most people, they like picking that going up is positive and down is negative. It really doesn't matter what you pick though, whatever you pick is fine. But if we pick up as positive, both the shell are dropping 14 meters, so that's got to be a negative, it's falling, and gravity is pulling things down, so this 9.8 has to be negative as well. So when we have a VI, a delta x, an acceleration, and a VF, what equation could we use from our motion sheet, our best friend? If we're looking at this, we could probably get away with equation number 6, and we can also notice that it's equation 6 here because we don't have time anywhere in this problem, and neither does equation 6 here. And that's saying that the final velocity squared equals the initial velocity squared plus 2 multiplied by an acceleration, which is our gravity, multiplied by some displacement. So if we go ahead and put in some values and solve this, our initial velocity squared, 0 squared, that's nice, plus 2 times the acceleration of negative 9.8 meters per second squared, multiplied by negative 14. This will equal the final velocity squared. We multiply all these numbers together. Note the negative multiplied by negative is going to make things positive, which is nice. So 9.8 times 14 times 2 equals 274.4. And we need to be careful because that's a final velocity squared. We need to get rid of this square here. And the way we do that is by taking the square root of both sides. And when we take the square root of 274, we get our final answer here for our final velocity to be a nice 16.5, and that has to be meters per second because that's what the speed needs to be. Okay, so not too crazy of a problem, but there was some hidden information there. We need to remember that at rest at velocity 0 at 0, and we always need to remember that gravity is an acceleration. It's pulling things down at that 9.8 value. Okay, so with that, this problem is, it's finished. Y'all take it easy, and adios. See you on the next one.